Hello, my name is Dragos Miron, and this year I've been working with Dr. Ellis Miller on a rather interesting problem: how to draw a graph. The input to this problem is represented by an adjacency matrix, shown over here, of a graph, and the end result should look like these images. First, we need to decide on what makes a graph look nice. After researching possible ways to represent a graph, we settled on the following metrics: 1. Symmetry, 2. Reduced number of edge crossings, and 3. Reduced sum of edge length. But we are primarily focusing on symmetry. Now the next question is, how do we obtain symmetry? And the answer to that question is automorphisms, which are defined as graph isomorphisms to themselves. Another way of saying that is that an automorphism is a mapping from the nodes of the given graph G back to the vertices of G so that the resulting graph is isomorphic with G. For example, if this is our graph G, a possible mapping for the graph is when 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to 1, and similarly 4 to 5, 5 to 6, and 6 to 4. The resulting graph here is an automorphism of the first graph. All the automorphisms of the graph form the automorphism group of that graph, and a way to represent this group is through automorphism group generators, like the one here. Using tools like Naughty, Saucy, and Bliss, we can determine the automorphism group generators, and they characterize the graph symmetries, and therefore are very useful for this project because we can obtain a nice graphical representation. The program allows the user to create a graphical representation in 3 ways. The first one is by simply clicking on a canvas area to create nodes. To create edges between those nodes, a user must click on one node and then on the other. The second way to create a graph is by importing a file which contains information about the adjacency matrix and optionally about the automorphism group generator. And thirdly, by using the edit mode, which allows the user to create an adjacency matrix and optionally an automorphism group generator. In this case, we will have no automorphism group generator. After, the user can save a file describing that graph or can draw the graph on the canvas area. To demonstrate how the program draws graphs, we will use the previously imported graph. The graph was drawn randomly as the random option was selected. Within this mode, we can swap nodes so that the number of crossings is reduced or to reduce the total sum of all the edge lengths. The second mode is placing the nodes randomly on a circle, and the same two optimizations can be applied. These modes do not make use of automorphisms and present no symmetry, but the following ones will do that. This mode places the nodes on a circle, but instead of doing it randomly, it clusters them as they are paired in the automorphism group generators. The ones that are not present in that group will simply be placed in an inner circle. To better visualize the clustering and to highlight the symmetry, the user can modify the distance between the clusters. The next mode clusters the node on a circle again, but the pairing is done differently. Cluster 1 will now be formed by grouping the first node of each pair, cluster 2 will contain the second node of each pair, and so on. Same optimizations apply. The last two modes cluster the nodes similarly to the previous ones, but the nodes are no longer placed on a circle. These modes will place the nodes from each cluster on an individual circle. The user can modify the diameter of those circles. Once the user is pleased with the graph, he can save a file that will remember the placement of the nodes. Or he can produce a JPEG image of that graph. The file created looks like this and contains all the information about the adjacency matrix, about the automorphism generator, and contains the last saved graphical representation of your graph. And this is how the image looks like.